In this video, we will use particle swarm optimization algorithm for the speed control of BLDC motor. So we start our code by clearing the workspace, clearing the command window and closing all existingly open figures. Then we open our Simulink model. I have made the Simulink model by the name of BLDC motor.slx. So we open the Simulink model. Let me show you that. So this is the Simulink model. As you can see, this is the transfer function model of BLDC motor, and the various parameters such as LA, RA, JSBV, KT, KE, all these parameters are taken as variable in the model because we will define the values of these variables in the code itself, and once the lines are executed of that particular section of code, all the parameters would be available in workspace, and from workspace our Simulink model can take these values and run the simulation. So these are the model parameters of the Simulink model. All the values have been taken from a research paper. Next, we move to problem definition part. Here we define the objective function. It is control BLDC. We have made a separate objective function file in which we are calculating the objective function value, and we are passing k vector in the objective function. This k vector is actually the vector containing the three PID parameters kp, ki, kd, which are also the variables of our optimization problem. And obj_fun is the function handle. Whenever we will have to pass the parameters in the objective function to find the objective function value, we will pass the parameters in obj_fun function handle, and from there the values will go straight to the objective function file, and this file will return the value of objective function. For our project, we are taking the objective function as ITSE, integral time square error. So the file would return the ITSE value for all the members of population for which the three parameters are passed in the objective function. Next, we define the global variables kp, ki, kd, which are also the parameters of our PID controller. Number of variables is 3, and then we define the maximum and minimum value of variables, that is the upper and lower bound of variables, and these are defined in the same order, that is kp, then ki, then kd. So kp is from 0 to 10, ki is from 0 to 100, and kd is from 0 to 1. Then we define the var size. It is the matrix size of decision variables, and the matrix size is 1 row and 3 columns because n equal to 3, and the 3 columns of course correspond to the 3 parameters of PID. Next, we define the parameters of PSO. So the maximum iteration is 25. Number of population I have taken as 40, and then the inertia weight. So the maximum value of inertia weight is 0.9 and the minimum value of inertia weight is 0.4. Then we define the acceleration coefficients. So the personal acceleration coefficient as well as social acceleration coefficient, both are taken as 2.3 C1 C2. Then we move to the initialization part. So here we generate the initial position of particles, and for that we first take the for loop, and each iteration of this for loop correspond to one column of k matrix. The k matrix is actually, this is the SIMOUT variable. In fact, this is the SIMOUT block. So this SIMOUT block is used to transfer the simulation data to the workspace, from where this data set can be used for calculating the objective function value. So this SIMOUT block would transport the two set of arrays. One would be the time instant vector and other would be the data vector. That is, in our case, this SIMOUT block is connected to the error signal. So the data vector would be the error values at those instants of time. So two arrays would be passed into the workspace variable, and we are extracting the data transferred from Simulink model to workspace in these two lines. T vector will contain the time instants at which the simulation data is calculated. So that is extracted using simout.time. This is the syntax for extracting the time instant values from simout. And to extract the error value, that is deviation in speed values, the syntax is simout.data, because since the error signal is simply a data for the simout block, and that data for us is the deviation, which is a unit step at time t is equal to 0.1 second. So remember that when the motor starts, there would be no load on it because there is no load torque. Load torque is applied at time 0.1 second. So at 0.1 second, the load is applied. So our controller will try to minimize the error in speed when the motor initially starts as well as when load is applied. Another very important block is this two workspace block, which has its default name SIMOUT. This block exports the Simulink data to workspace, and from workspace, this data is used by the objective function file to calculate the cost value of each ant. When Simulink is run for a given time period, let's say from 0 to 0.2 seconds, then our Simulink has some ODE solvers which calculate the response points at different instants of time in that period to draw or plot the response in scope window. For example, if we draw any graph, we take some data points, join them, and graph is made. In the same way, Simulink solver calculates the data points at various instants of time and join them to plot the response, which we can see in this scope window. So this two workspace or sim out block will export the data points of, since we have joined it into the error signal, so it will export the of data points vector of error signal as well as a vector of time instants at which those error points are calculated to the workspace, and from the workspace we will extract the data in objective function file, which has its specific syntax for extracting the data that I will show when we write the objective function file. Using those data points, objective function will calculate the cost value or ITSE value